Welcome everybody on Zoom. Welcome everybody in the lecture hall for another week of big data. So what's on the menu today? We are going to continue our journey rebuilding the technology stack. What we've done last week is cloud storage. It's the first way of storing data. It's typically services that you have on the clouds by Amazon, by Google, by Azure. So you have all the big players. They all have some form of cloud storage that allows you to store data sets. So before we start, I have a question to ask you as always in order to check your knowledge. Actually, I think I have two questions, and then we'll move on with the remainder of the lecture. All right, so go as always to this address right here, or if you prefer, download it to your smartphone. Let me move over. So this is today's question. These are 4 different propositions, and I'm asking which one of these cannot be stored as an object in Amazon S3. Is it the first episode of Star Trek Discovery? Is it the 300 petabyte data set containing proton collisions released by CERN? Are these the static pages of a website, or an archived backup of your 2 terabyte hard drive? Still have answers coming in, giving you a bit more time. So are we going to break the 100 barrier? And yes, we do. All right, wow. There is a majority, and there is a very big majority. So you seem to almost everybody agree that the one that cannot be stored is the 3 as a single object, right? The answer says as an object. So the 300 petabyte data sets with the proton collisions, why is that? Yes? Exactly. You have these 5 terabyte limits, and you cannot store anything beyond 5 terabytes as a single object. Regarding what you can store, as I said, it's a black box. An object is just a sequence of bits, so it can be absolutely anything that you can represent as a sequence of bits. So this is why you can have a backup, a video, anything. In fact, this is used, as I said, by streaming services like Netflix and the like to store the chunks of the videos and download in real time as you need them. All right, very good. It's always nice to see a majority like this. Now, let's move over to a different one. What is the best practice? So basically, in which order should you handle things? Try to scale out, then try to make the code better if it doesn't work, then try to scale up. Or try to make the code better, then scale out, then scale up. Or try to scale up, then scale out, then make the code better. Or the order doesn't play any role, one should just try everything. All right, we have a majority again, and the majority says, try to make the code better, then scale out, then scale up. So indeed, this is something, it's almost the first thing that you would need to learn anytime you deal with big data. What a lot of people do not realize, especially when they create a new startup or a new company and they are going to analyze data, they think, okay, let's go NoSQL, let's go for a cluster of machine, and then it's too slow, so you add even more machines. But the thing is, in many of the use cases, I would almost say 80% of the use cases, first, the data fits on a single machine. And second, you can actually write the code in a way that is more optimized than you typically start with. So what I'm saying here is, do not underestimate what one machine can do, what your laptop right here can actually do with the data. There is already a lot you can extract from one machine. And you should go to a cluster if you really have good reasons why your machine is not good enough. Typically, the one reason would be that you cannot read fast enough from the disk. It's really the disk input-output. Then you go to a cluster of machines, so you scale out the number of machines because it's cheaper. We saw that there is a linear cost in scaling up out the machines, and scale up as opposed to scale out. What is scale up? Well, how is it different from scaling out? Yes? Exactly, you make the hardware more powerful. So that means that you put more CPU on a single machine, more memory, and so on. Yeah, absolutely. And this doesn't scale linearly because it's, the more you try to add memory or CPU, the more expensive it's going to get for a single machine. All right, great. All right, so that was our recap. I'm going to move on back to the slides. And we'll continue. So 2 weeks ago, we had a recap on relational databases. We saw that a lot of data actually fits in relational tables, and that would be the way to go. We looked into scaling out in order to use more machines. In fact, it's just the beginning of scaling out, because what have we scaled out for now? It's just the storage. We've just looked at cloud storage, either as object storage or key value stores. So this is just the beginning. We're going to scale out during weeks in this lecture. But we need to rebuild everything with a scale out in mind. What we also looked at is a model called the key value model. It's actually the model that was common to the two things we did last week. It's both for object storage, where you have object ID. So for Amazon, it's bucket ID plus object ID. For Azure, it's account, container, and I forgot the blob, probably blob ID, or the partition ID. You see, even I don't have a perfect memory. So we've seen object stores and key value stores, and they both share that super simple model, much simpler than the relational model, much simpler than the sort of data models you have on the high level. In fact, that's the way things usually start when you want to scale out. You need to do something super simple, simple enough that it's almost magic to scale out. But of course, as I said, it's just the beginning, because you need to add back all of this technology on top to get the kind of functionality that you have in a one machine relational database. So the data that you want to store in the clouds or on any storage level, that data can either be raw data, so it's the sort of data you get from sensors, from the collisions at CERN, for example, but it's also to store derived data. So the derived data means the data that you have obtained from a query on the raw data, right? So you took the raw data, you read it, you ran some analytics, and then you output something back to cloud storage, and you get derived data. Then you can do it once again, so you can have multiple levels of derived data, right? So you just have to have this in mind, that it's for reading and writing data in the storage. Okay, but now, why are we yet again looking at a storage topic today, right? Why is cloud storage not good enough or not the only game in town? There is big data and big data. So the idea is that last week, we looked into huge collections of large files. Large, up to 5 terabytes, as we saw, but huge. Why? Because cloud storage typically is a worldwide service, right? Billions of users who can store their data in there. So it's absolutely huge. Today, we are going to look at a large amount of huge files. It means we are going to break the 5 terabytes barrier. How? We'll see. And we are going to, as a compromise, we will support less files, typically the same order of magnitude as you would have maybe on your hard drive, closer to that than to the sort of things you have in S3. All right? So now quantifying things a little bit, here we could save billions, and I could even have said trillions of terabyte files versus millions of petabyte files. We can actually store petabyte-sized files in the technology we'll see today. So I put again here object storage, because that's why it's called. Just object, right? It's not the case for key value stores. In DynamoDB, you cannot store terabyte values. What's the maximum size in DynamoDB of an object, of a value? 400 kilobytes, right? I didn't hear what you said. It's the right order of magnitude. You know, what's important is the order of magnitude whenever you learn things. So 1 megabyte, 400 kilobytes, it's pretty much the same, right? So you're exactly on the right estimate here. I also talk again today about the orders of magnitudes. All right, and here that would be file storage because it's closer to a file system. All right, so now if we put these two technologies, so this is what we've done last week with the key value model on object storage. And today we look at a file system using block storage. That's actually the secret to break the 5 terabyte barrier. All right. Do we have questions on Zoom? Because I see the little, no questions. Okay. So the predecessor of the technology we'll see today is called Google FS for Google File System. Why was it invented in a company? So because they had issues that you have at large scales. It's because if you use a single machine, or that's one of the ways to look at it, if you use a single machine, it might crash once in a while. Who already lost all the data on their drive because of a crash? So you see, it happens, but not everybody. It didn't happen to all of you. This is the difference between a single machine and a cluster of machines. Because in a cluster of machines, you just can be sure that the machines will fail. It's a future tense, they will fail. In fact, not only will they fail, they just fail all the time. In fact, you have full-time employees in data centers who spend their days replacing parts in the servers because it keeps failing. So if you design a system that's going to work in a cluster with hundreds to 10,000s of machines, then you need to make sure that that system is going to keep going even when, not if, when the machines fail, right? So this is one of the requirements. So you need some sort of monitoring. You need to detect errors based on the monitoring. You need to automatically recover if like a drive crashes and so on. And then what you have is a fault tolerance system, right? It's also the spirit of the CAP theorem, right? That we want to be available at all times and be consistent. All right. Now, in terms of read, excuse me. In terms of read, you have to understand, your computer scientist, so you know that, right? That you can access your hard drive on your computer, random access. You can read from anywhere in your drive. That's actually the difference with the old machines that we used to have on tapes. When you have a tape, you need to actually roll it all the way to where you want to be, right? So that's not exactly random access. But we have the luxury today with hard drives and with RAM that we can randomly access anything, anywhere. We could, in fact, ask for a specific bit, but of course, we read in blocks, right? 4 kilobytes at a time. But it can be anywhere. Another access pattern that is different from random access is to scan the entire file. It means you start at the very beginning and you go all the way to the end. This should remind you of a tape. This is what you actually do with a tape. The same goes with writing, because we saw we also need to write back our data. That's for the intermediate derived data sets, right? So it's the same for writing. You can actually write anywhere on your hard drive, on your laptop. But in some other cases, you might have a system that is designed to allow you to just append things. You can only write at the end of the file and add things, but you cannot modify what's already written. And in fact, the systems like today's system, they are optimized for this, for scanning through the entire file and from appending at the end of files. We drop the requirement of random access. We are not going to even try to build a system that allows you to efficiently read randomly and to efficiently write randomly. All right. Of course, you could argue, but if we have this, we can also do that, because if you want random access, just start reading from the top of the file and then go to the place you want, right? But the point is it's not efficient. So this is about not efficiently supporting random access. Okay. Appending and scanning is in fact super useful for big data, because if you append, this is exactly what you get like at CERN. If you run the collider and let particles collide, you just keep logging and logging and logging. So you're just accumulating data. So what comes from sensors, logs, intermediate data, it's all written as append. Even intermediate data, I mean the output of your queries, we'll see in a few weeks how we do that, even that is just appended. You just write like that. And the same goes for reading. When you scan the file, this is actually the way that you do data analytics. You're going to just scan the whole data set. And this has to do with the fact that, as I said, so two things here. First, I said that one of the primary reasons why you need to not drop your laptop, don't break it. You need to give up working on your laptop in order to use a cluster. It's because of the I/O bottleneck. You cannot read fast enough, so you are going to be reading from the cluster. And because this is the reason we use a cluster, we are going to very often have use cases where you just scan the entire file. Yeah, and the other reason, if I didn't forget it, so the I/O bottleneck, and the second reason is batch processing, is that we are not going to analyze data looking at small places everywhere, but when we analyze a data set, we just read through the entire data set. All right. Another feature of the system we want to build today is that we want plenty of people to access it in parallel. So you're not the only one. Plenty of people are using it. However, we are not looking at a worldwide scale. A very important difference is it's not a worldwide service. It's more like an installation within a company or within a university. You have a cluster, you install the distributed file system, and then the people within your company are going to use that system, right? So it's a slightly smaller scale. But basically, you want the people to be able to use that system. And if they write at the same time or read at the same time, that shouldn't interfere too much, in the sense that they should still get, in some meaning of the term, consistent reads, right? And if you write, then you need some sort of lock on what you are writing to avoid some race conditions and that kind of issues. All right. And here I'm going to repeat again something that I said, because that's actually not new, but it's here. The top priority is the throughput. We want our system, when it's in cruise mode, when it's working, we want just bits to flow. This is what we want. Throughput, throughput, throughput. We want data to flow around. We do not want the system to be bound by latency, in the sense that most of the time is spent waiting for things, right? So we want a throughput-bound system. I'll say more also in a few weeks on the idea of bottlenecks and CPU-bound, memory-bound, and so on. So we want a system that's very, very good at just letting data flow, but the latency is secondary. Actually, the latency is not really great of what we are going to build today. You can even experiment it when you play with it. All right, this is something I showed you 2 weeks ago. It's this mismatch between the evolution of capacity, that's all we can store, the speed at which we read it, and the latency. And the problem was that we had a discrepancy because we cannot read it fast enough. So we just parallelize. You just read in parallel from 1,000 machines. The system today that we built will allow us to do that. And the second thing is that between latency and throughput, because the latency, so what you need to wait for every time you want to access data, it's only improved by a factor of 150 since 1956. as opposed to throughput by a factor of 10,000. So the secret here is that instead of doing it bit by bit randomly, you just process batches, right? You take an entire batch of data and then process it in one go. So that's batch processing. Parallelism and batch processing, this is going to be all over the place during the entire semester. Okay, but now let's get back to this system. So I told you it's Google FS, GFS, the original system. This is a proprietary system. But later, there is an open source version of it that was invented that's called Hadoop. It's the name of the elephant toy of the child of dog cutting. This is why you have this little elephant right here. And it's called Hadoop, right? Who heard of Hadoop? I'm pretty sure a lot of you. Right, so since we have a majority. All right, so Hadoop comes slightly later than the Google work. It's a series of several technologies that originated in 2006. And it contains three things, mainly, that we will in fact cover in that lecture. First, the distributed file system called HDFS, Hadoop Distributed File System. We will go at length about that in this and the next hour and tomorrow. Then there's MapReduce. I'm pretty sure everybody heard of that. So it's also from Google, right? But there is a Hadoop implementation running on top of HDFS. This is for in a couple of weeks. And then we also have the white column stores that are just bigger tables, right? And HBase would be the technology. This is all open source. We'll study these two in a few weeks from now, and this one today. This is the Google side of things. So GFS would be the one that each HDFS corresponds to. MapReduce, they didn't change the name here, so that's the Google MapReduce and the Hadoop MapReduce. And for the third one, Bigtable was the pretty cool name that they came up with at Google, and then HBase was the open source equivalence. Okay, and here, this is just to show you the evolution of things. I didn't manage to go past 2016 because it seems that nobody actually continued using these technologies because things go so fast, and we actually will see that there are newer technologies. But basically, this is the size of the cluster, so the number of machines. So back then, that was 15 years ago, they were at a 3-digit number of machines, like 100, 200. And then you see how things accelerated all the way, 10,000, 24,000, 42,000. And this is the sort of data that you can process, right? So 6 years ago, they were at 600 petabytes of data sitting on a cluster of almost 100,000 machines, right? Do you remember why we are limited by 100,000 machines in the same data center? Yes? Yes, exactly. And electricity, exactly. Cooling and electricity, these are the two limiting factors. Okay. Okay, well, this was just the introduction, right? So far, I didn't really go into technical stuff. That was just the motivation of things. But now we are going to go into the details. I'm going to do it in a way that almost will be the same every week. I'm going to start with the logical model on a high level, and then I'm going to show you the physical implementation. This is also the spirit of data independence, right? And also you're computer scientists, so you know why these things are good, right? To have a modular architecture with always nice APIs and layers. So I'm going to start with the model. You will see that the model is actually pretty simple. That's actually why it's a good model. All right, so the key value model is what we saw last week, where you just have keys associated with values. We are going to reintroduce today the same things you have on your local laptop. We will have a file hierarchy. So in HDFS, you have directories and files organized in a hierarchy like that, just like you have on your laptop. So it's very intuitive, all right? The second thing is object storage was a black box. When you use S3 or blob storage or even DynamoDB, the object is just a sequence of bits. I'm saying it's a black box, but again, you remember that it doesn't mean you cannot have parts, right? I said in S3, for example, if you have a very large object, you can still upload it in several parts and then paste it together at the end. But the model is still saying that an object is a black box. In HDFS, we are going to have blocks. Exactly like on your local laptop, we are going to store the files using blocks. This is how we break the 5 terabyte barrier, actually. All right. Now, I said things are simple, but of course, something needed to be a bit more complicated. You know what happens when there's plenty of technologies and plenty of people working on things is that people start calling things with different names. So it means that there is some sort of concepts that we'll see throughout the lecture in almost every week to designate similar things, actually to the block. But we'll talk about chunks, splits, shards, partitions, and so on and so on. This is all the idea that you take something very large and you just slice it into smaller pieces, smaller chunks, right? So in the case of HDFS, it's blocks. In GFS, so this is the Google version of HDFS, they called it chunks, right? But it's the same thing as blocks. Splits, we will see that this is how MapReduce calls the partitions. Shards, I think I already used that term last week when I explained that when you store data sets, it's a very common way to not store it as a single file, but to actually have a directory, and then you have files with increasing numbers, like file 0, file 1, file 2, and so on and so on, right? So these are called shards, typically, when you store your data that way. Partition is kind of the neutral name. Typically, on more of a physical level, we would call it partition. So do not be scared by all of these terms. Just understand that they mean more or less the same things. Nevertheless, it's always a good idea to try to remember which is for what, because if you start talking about HDFS with shards instead of blocks, then people will be confused, right? Because they're still used to talk about blocks. Okay, so having said that, we have a file hierarchy and we have blocks. The way the model looks like is that we have this hierarchy of directories and files, and every file is associated with a sequence of blocks. And the blocks are just bits, and that's it. That's the HDFS model, right? So you see it's slightly more complex than just object storage because we have this hierarchy and the blocks, but this is HDFS. On the logical level, that's all there is to know. Okay, that's pretty simple, right? Who finds it easy? Okay. So thanks to the blocks, the files can fit beyond the single disk. So a disk is maximum 26 terabytes today. We can fit petabytes now because we just have plenty of blocks. And the level of abstraction is very simple, right? We don't even get into the sort of things you see in systems programming, right? The inodes and all that kind of stuff. You don't even need to worry about that. This is really higher level. Okay. A benefit of the blocks is also that it gives you what I will almost call liquidity. Because when you have plenty of blocks, it's easy to just spread them all over the cluster, right? You just put them on the machines and even you can load balance across the nodes. All right. So now, what is the right block size? For a single machine, we saw that it's roughly 4 kilobytes. And again, it's the order of magnitude that matters. 4 kilobytes. Some file systems might have 8 or 16 and so on, right? Relational databases actually typically on a single machine use higher block sizes like 16 or 32 kilobytes depending. Okay. But of course, it's going to be too easy if I just tell you what the size of the block is, right? So I'm just going to ask you and see what you think about that. So here's the unsurprising question. What is the size of a block in HDFS? And here again, it's about the order of magnitude, right? 32 kilobytes, just like in a local file system, I actually picked the relational database kind of blocks. 128 megabytes, which is a good compromise between latency and throughput. 2 terabytes, because that's what you can fit reasonably on any modern hard drive. Or 512 petabytes, because it's big data. So what do you think? Oh, wow. The numbers are even bigger now. We are past 110. Okay. And the majority is correct. It's 128 megabytes. So now, of course, I will owe you a few explanations of why that actually is. It has to do with throughput and latency, again. Let's eliminate the answers one by one in order to understand. 512 petabytes, you can forget about it, right? It would be insane to have a block of that size because you would basically, for most data set, have a single block. It doesn't even fit on a machine. So then you're back to square one on how do I actually then spread the block over multiple machines. No, you want a block to fit on a machine, right? A block must fit on a machine. So that eliminates the fourth one. Now, why not 32 kilobytes and why not 2 terabytes? The intuition here is, imagine as a thought experiment that we use blocks of 32 kilobytes. And we try to store a file, let's say even a 1 terabyte file. Or I'm going to try to keep things simple for my poor math. So let's say 32 terabytes. A 32 terabyte file with 32 kilobyte blocks. So how do we go from kilobytes to terabytes? So mega, giga, and terabyte. So that's a factor of 1 billion for going to from kilobytes to terabytes. So we are looking at 1 billion blocks. Imagine that every time you access a block, you have latency. Every time you have latency. So having 1 billion times latency is just enormous. You're going to lose a lot of time waiting for the blocks to arrive or to be read, right? Even if you have, let's say, 1,000 machines, you will still have to access a million block on every one of the machines. That's a lot, right? So here, that system would not fulfill the requirements because we said we want the data to flow in our system. We don't want the issue to be the latency. So this is why 32 kilobytes is not good enough for this system. 2 terabytes, it's the opposite. 2 terabytes, if you had blocks of that size, it's not spreading enough on the machines, right? You would very quickly you would not, let me put it that way, you would not use the potential of parallelism well enough if you take 2 large blocks. All right? Or let me put it that way. If you use 2 terabytes or 120 megabyte blocks, the latency issue will not be worse with 128 megabytes. So this is why we go for it, because it allows us to spread more over the cluster. All right. We go back to the slides. Oh, what happened? So again, normally I prepared copies of the, get me exactly where I was. Let me try this one. Yeah, this is where we were. All right. So now, the order of magnitude matters. It doesn't matter, it could be 64 megabytes, could be 256 megabytes. In fact, with the evolution of the hardware, there are some systems that are already using a gigabyte or even 2 or 4 gigabytes for block sizes. In Azure Blob Storage, they are actually at 4 gigabytes. So it's really the order of magnitude that is important. Kilobytes, that's wrong, not enough. Terabytes, that's too much, too large, right? So this is the sweet spot. Okay. Now that we have the block size, let's go into the architecture of HDFS, meaning the physical architecture. So how do we connect the machines with one another in order to make HDFS work? So we could use a peer-to-peer architecture. In fact, this is what we had for DynamoDB and the core protocol and the key value model, right? But in our case, we are going to be using a centralized architecture. It means that one of the machines is actually singled out. I'll call it the coordinator, but just need to be aware that there's plenty of other names that people are using. So we have a coordinator node that is acting as some central place that coordinates everything. And then we have all the machines that I'll call worker. Here also there's plenty of other names. And the workers are actually doing the work, right? We'll see what that actually means in a bit. All right, and so the architecture of HDFS is a centralized architecture just like that, where we have a coordinator and workers. Now, they have names. The coordinator is called a name node. You need to remember that by heart, the name node. And the worker nodes are called data nodes. So there's one name node and plenty of data nodes. Well, the names probably already give you a hint about what's going on, right? Because if they are called data nodes, then as you can imagine, this is where the data is. And when we say data, we mean the blocks, right? So the blocks are going to be here, right? Okay. So what that means now, if we take a single file and look at how it's stored on HDFS, we saw from the logical model that I told you about earlier that the file is divided into chunks that we call blocks, yes? So it's divided into blocks of 128 megabytes. And these blocks are then put on the data nodes, but replicated. It means that every block by default is going to be stored 3 times on 3 different machines. All right, so we replicate everything. We replicate because of fault tolerance. We said that drives will crash. So if you only store a block once and the drive crashes, you lost it. In order to lose a block now, you would need 3 hard drives to crash at the same time. So the odds of that are pretty low. And if you really, really have sensitive data you don't want to lose, you can change that. You can also make it 5 or 10, so you can actually change the replication factor. Right. Something also important about the replication of the blocks is that there is no such thing as a main copy of the block, like the block, and then the replicas. It's not like that. There's just replicas of the blocks. There is no first or second or third. It's just 3 replicas of the block. There is, in fact, an order, but it has nothing to do with the logical model. It purely has to do with physical aspects. Okay, so we have this architecture where we have the name node and all of the data nodes that are right here that are accessed by people.
Yeah, there's a question on Zoom. Is the name node like a centralized node metadata store? And is it replicated?
So yes, the name node is centralized. There is only one of it. We will actually get into the issues that come with that. So let me be more precise and say, in the first version of HDFS, there was just one data node. In the first version of HDFS, there was just one name node. Right. But then, because of the issues, we'll actually talk about that probably later today or tomorrow, we can actually add a few more to help out with the name node. But technically, there's only one.
Yeah, does name node contain no data, just metadata?
Yes, exactly. There is no data on the name node. There is no blocks, not at all. It's all about metadata. What metadata? I want to keep it as a cliffhanger because we are going to actually see exactly what there is on the name node, right? Very shortly. So I'm going to show you everything regarding this. Yes?
Wait, maybe just
sorry. Yeah.
One.
Let's see. There you go.
So if we also have no order among the blocks, when we want to access one of them, how do we, which one do we sort of access?
So typically, what's going to happen is that you sort the blocks by distance from where you are. Let me explain. I will come back to that. So I'm going to just keep it quick for just this answer, and then we'll see more details probably tomorrow. Very often, when I say you, I mean a machine on the cluster. The client is typically going to be a machine on the cluster. What happens typically when you create a cluster of machine is that you use SSH to log into a machine there. So you are going to, I don't know, maybe you log in and this is the machine where you log in, right? And if you log in on that machine, then you probably notice that there is a node right here that's on the same machine. That's probably the one going to be the one you will use. Maybe next, there is another one not so far away and maybe some further away. So you are going to prioritize the blocks that are the closest to you, right? But I'll come back on that and explain what does it mean a distance, even though you can try to guess based on how I showed you what there is in a data center, right? But the rule is by distance because you want things to be as quick as possible. Right? Yes? Yeah, we can give the catch box.
So you design the data nodes to be fault tolerant, like you can still access data when it crashed, but like for the name node, if the name node crashes, then how are you going to manage that?
So that's a very good observation. Let's first talk about the data nodes to make this precise. An individual data node is not designed to be fault tolerant. It's the system as a whole that is fault tolerant. What I mean by that is a data node could crash. The machine can just go away and the data node is just gone, right? But the system is fault tolerant because you still have replicas on the block on other machines. For example, here, if I just let me, well, don't manage. Let's say that the 3 here crash. We still, we were very unlucky. We still have a copy on the green block here, a copy of the blue block, and so on. So you see, we have copies at other places. So a single data node is not fault tolerant and can go away at any time, and they will go away once in a while. But the whole system is fault tolerant. Now, the name node is a different thing, because indeed, you are right that the name node, we call it a single point of failure. Basically, with this kind of architecture, if the name node goes away, we have a problem. Because it's the name node that kind of knows what the blocks correspond to and how to assemble them. We'll look into more details later. But basically, yes, you have a problem if you lose the name node. This is why there are solutions that were carefully engineered to address that, and we will discuss them in the lecture. Yeah? Other questions on Zoom?
I'm following up, I'm checking. Wait, I cannot hear myself. I'm waiting for them. So is there just one name node that holds the entire metadata?
Yep, at least in version 1, but again, we'll discuss that. Yes, there is just one.
Yeah, and the other ones were answered.
Yep, all right, very good. I actually notice it's already close to the break. Any other questions? Otherwise, we'll just call it a break and then. No questions on Zoom too? Last call on Zoom? Okay, okay. So let's take a break and we'll be back in 15 minutes at 3:15 and continue with the lecture. Thank you.